Thank you, John. I think everyone's right. It does feel good to be part of something new and something that should have an impact. If you were here at the beginning of John's presentation when he was fiddling with the microphone, those were in fact electrodes. And this is in fact to set them off, just in case he decided to say something politically incorrect. But he was pretty good, I would say, throughout the whole thing. Anyway, I have the pleasure to introduce Suzanne Stutz. Suzanne is the project manager for the new public health products within BASF and Global Public Health. With a PhD in organic chemistry from the Max Planck Institute for Medical Research in Heidelberg, she has more than 20 years of experience in product development and marketing. For the past 10 years, Suzanne has been focused on public health products like long-lasting insecticidal nets and other vector control products. She has a strong interest in public-private partnerships, working closely with research from LSHTM and IVCC. So, Suzanne.
Yeah, the clicker. Okay. My microphone works. Good. Thanks for the introduction. I have the pleasure to present our new dual net, which is Interceptor G2. And before describing that net, I just want to make a historic wrap-up on LLINs. So on top you see the graph with the deliveries of LLINs into the world, and it's an amazing story. It started in 2004, and in 2014 we had the biggest volume, over 200 million LLINs delivered in 1 year, and I think in 2017 we will hit that mark again. So since 2004, 1.5 billion LLINs have been delivered. And now it comes down to the active ingredient. If you do a little bit of calculation, take an average size, take the different types of LLINs, you end up with something between 1,300 metric tons of pyrethroids to 26,000, depending which type of net. So it might be somewhere between 5,000 to 10,000 tons of LLINs put into the field since 2004. For your comparison, how much that is, you look at the IRS that has been reported by WHO, and in total between 2000 and 2009, 1,500 metric tons have been put into the field. Why am I telling that? LLINs with pyrethroids are just perfect to put them onto the net. They have a very low toxicity to humans, so are safe to use. It's very cheap, it's readily available, and they're very good in killing. They're neurotoxic, they give a good knockdown, they act as repellents, and the chemical profile is just perfect to put it onto an LLIN. They're solid at room temperature, they are very insoluble, so they survive the 20 washes, and they have a very low vapor pressure, so during the production process you don't lose them. They're easy to handle, you can put them on the net, you can put them in the fibers, and you can use standard textile production processes. So they are just perfect to put them on. And this was a very high level to compete with. But as I said, the large amounts of pyrethroids put into the fields have a cost. And this is another way of talking about resistance. I'm going to make that very short. You see, we have seen a development of resistance over time. And in 2015, a lot of red dots are now in the picture. This is where chlorphenapure, and I thank Luke for the introduction of our product, comes into the picture. It's Pyrol. It is BASF technology and has been launched in 1995. It is accessible and registered in over 40 countries, mainly for pest control, so it can be used in food handling areas like kitchen or food storage. It is a repurposed active ingredient, and it's new to public health. And it belongs to the IRA group 30. It's an uncoupler, and it has a very unusual mode of action, which is different from all the active ingredients that you see in public health. It's non-neurotoxic. It is a pro-insecticide, so it needs to be metabolized first, and you need to cut off that part of the molecule to get to the toxic form. And it disrupts the energy generation in the mitochondria, so non-neurotoxic. And tests of the London School have shown that it has no cross-resistance to other active ingredients. And the advantage of it, and this is the last point, and this is very important, the chemical profile is very similar to the pyrethroids, talking about it's solid at room temperature, it's very low soluble, so it survives the 20 washes, and it has a low vapor pressure. So it was really encouraging to put that onto a net. As I said, it's non-neurotoxic and it's non-repellent. So our idea in the beginning is, what do we do with that? You need a personal protection from a net. And this is something that you have from the pyrethroids. So you see here, this is the advantage of the pyrethroids, your personal protection. Chlorphenate doesn't give that. But it works very well in killing resistant mosquitoes and disrupting the transmission. So there you have your pluses here. So the logic way was you combine both chlorphenate and alpha-cypirethrin. And this is leading us to interceptor G2. What is interceptor G2? It's a coated LN, so we put our active ingredient on top of the fiber. It contains 200 milligrams per square meter chlorphenate and 100 milligrams per square meter alpha-cypirethrin. And it's designed to kill resistant mosquitoes. And you see that has been the fruit of a very good cooperation between BASF developing the net, between the London School testing it in the field, and the IVCC funding these biological tests. So that was very fruitful, and I'm still grateful for that. What have we done after that we had developed the net? We put it in the field and had done several HUT trials. We did WUPES analog HUT trials in Tanzania and Benin and Burkina Faso with London School and the IRSS. We also had done 2 WUPES 2 trials in Tanzania and Ivory Coast. And the setup is basically you compare unwashed with washed nets. The intervention arms is interceptor G2. And as a comparator, you have interceptor 1. I call it interceptor 1 or interceptor. And this is our standard net containing 200 milligrams of alpha-cypirethrin. You compare it also with a dipped chlorphenate just to have the other active ingredient on a net. And you compare it with an untreated net. And now I'm going to show some results. So these are the results from Benin. On the graph on the left-hand side, you see the 72 hours mortality of wild free-flying mosquitoes, in this case Anopheles gambiae. And you see in Benin we have quite high resistance. The interceptor 1 with the alpha only is giving only something like 20% control, a little bit above the control. But the interceptor G2 is giving a kill of nearly 70%, which is really, really good. In blood feeding, you see that both nets are comparable, so the personal protection is there. These are the results from Burkina Faso, where we have even higher resistance. And you see again the interceptor G2 on the right-hand side, washed and unwashed, gives nearly 80% of mortality. And on the right-hand side, you see that the blood feeding is a bit lower than with the interceptor 1. So this is very encouraging. And I have a third HUT trial. So you see also that it works on Anopheles funestus. This is now in Tanzania. And the resistance is not as high as in West Africa, but the interceptor G2 on this here improves again to a very good mortality of about 70%, and blood feeding is about the same in both cases. Why did I say 72 hours of mortality? You have heard Luke's introduction already, that when you have a different mode of action and we are non-neurotoxic, it might take longer until it kills. But this slide is to show you that we have not seen that in the field. In the field where the mosquitoes are host-seeking, when their metabolism is active, when the metabolization of the active ingredient to the active form is really fast, we see that it kills as fast as other nets too. So on this slide, you see on the left-hand side the unwashed nets, on the right-hand side the washed nets, and the left-hand bar is the 24-hour mortality, and the full bar is the 72. And you see there is not much of a difference. And I have another slide to give you the reference also with all the nets that we have. I'm sorry, it's a little bit busy, but you need to look only at the red line, which tells you how much of the kill was done in the first 24 hours. And you see that, for example, here in Burkina Faso, 95 to 97% was done in the first 24 hours. And if you go to somewhere where it's a little bit lower, like here, you see that also the interceptor 1 was acting slowly. So based on these data that we found here, we can say if you put it in the field and your mosquitoes are active flying around host seeking, it's not a slow acting ingredient. It acts after 24 hours. So to summarize a little bit on what we have with interceptor G2, it has a comparable blood feeding inhibition and personal protection that as a standard pyrethroid LLIN. It kills the mosquitoes with the same speed as a pyrethroid LLIN. It is a wash-resistant formulation. You saw the results between unwashed and 20 washes is not much difference. It's safe to use, is as safe as a pyrethroid-only LN, and it improves the killing of insecticide-resistant mosquitoes, which is its most important features, and it works on different ASTMH. So it has a potential to work also where vectors are insecticide resistant. We recently got a WUPES interims recommendation, and VCAG also noted that it outperformed interceptor LN. Something that is not on here, but that Luke already mentioned, is that we need to do epi trials that VCAG asked us for. And the reason is its new mode of action. I have put together this slide because Nick asked me what were the challenges you were facing during the development. Because we were fighting sometime during the process of the project, we were fighting very hard to get it to work. And it was not the development of the net itself. It was to understand how a different mode of action works and how it works with the tools that we have for testing nets. And one of the major tools that is used in every lab is the cone bioassays with 3-minute exposures on LLIN. And I have put together here 2 different graphs. When you look on the left-hand side, you see the cone test with the Kisumu, and you see that the alpha that is in the mixture is doing the job. If you take collected mosquitoes in the field, from the field, which are resistant, you see that the alpha basically is not working anymore. The interceptor LN is giving very low responses, but the interceptor G2 looks the same. Yeah? So we do not meet WUPES guidelines here with the 80% mortality. If you go then, and this is the advantage of testing LLINs, into a tunnel test, you get over 90% control because there you have your freely moving mosquitoes host seeking overnight, which resembles very well what you find in the HUT trial. I mean, I have on purpose shown you the HUT trials before the cone test, so you believe me that it works in the field. But if you start a development work, having only small pieces from the lab of the LLIN and doing your cone tests, and you find something like that, you first think your net is not working. But it was the other way around. The cone test is not resembling what we found afterwards in the HUT. And that was very, very hard to accept because WUPES tests are working everywhere. We could prove it's not like that. Yeah? So what we then basically asked WUPES for is that we need some flexibility in the evaluation because we can show with all the results we have collected, in that case, with that mode of action, a cone test does not resemble what you find in the field. So it is very hard. That was the hardest point to accept, that something that has been known for so many years and decades is working like a cone test is not working here. And another challenge I have put up here is on the same problem we have with IRS. And thanks also for the introduction of Luke, who has talked already about that. So this is a HUD trial that has been running now for 12 months. It just finished. So you see the chlorphenapyr IRS is giving quite good results over time. So for comparison, you have here on the right-hand side the bendiacarb. Now, if you look on the right-hand side, I have put here the in situ cone tests with Kisumu. And there you have the same problem. Basically here, you don't meet the 80% mortality because it's not a neurotoxin and it needs to be metabolized, as I just explained. So here we struggle that we don't have a tunnel test to test it. And the result is basically, and the brand name is Solando, is that WUPES commented that we have evidence that it might work, but we need to collect more data to show that it's really a valuable tool in the vector control, which we definitely believe it does, because chlorphenapyr is something new, because it's non-neurotoxic, but it's not easy to prove that. So I leave you with the challenges, and that was the end of my talk. Thanks for your attention.